Okay, I wanted to discuss something today that tends to be a sticky point for some people, and that is the concept of moles and molarity and percent solutions. And I want to start by simply let's maybe do this. We're going to try and answer this question. How much salt, sodium chloride, is in a 500 milliliter IV bag containing normal saline? And the concentration of salt in normal saline is 0.9%. Now, I don't want this to be too daunting. We just need to make sure we understand what all of these terms mean. And first and foremost, I would like to introduce you to the concept of concentration. You see the word, you're like, oh yeah, it's very concentrated, it's not very concentrated. People don't really understand what this is. Concentration simply is a ratio. It's going to equal a ratio of stuff, so the number of stuff, we'll say hashtag stuff, over a given volume, right? Concentration equals stuff over volume. It's just a ratio. And if we understand that, then understanding how to solve these questions is actually quite simple. That stuff could be in lots of forms. It could be in weight, or it could be in number, for example. Consider it's lunchtime. Consider a pepperoni pizza. I've got this big pepperoni pizza, and let's say there's 100 pepperonis on that pizza. I could say that the concentration is 100 pepperonis per pizza. And then intuitively, if I cut that pizza in half and ask you how many pepperonis there are, it's obvious, right? There's half of them, there's 50 pepperonis. I could also say, well, there's 5 pounds of pepperoni on that pizza. Same thing. If I had half the pizza, I know half the pizza has 2.5 pounds of pepperoni. If you knew that 100 pepperonis equals 5 pounds, now we've got a conversion factor, and I can actually tell you how much each pepperoni weighs, which is a lot. That's a bit of an exaggeration. But you see the point. So it's just a ratio of stuff, whether that stuff is in weight or mass or number, it doesn't matter. It's stuff over a given volume. That's concentration. So as we look at this problem in particular, we see that we have volume. Here's volume, 500. Oh, that's way too big. There's my volume. Okay, done. We're looking for how much stuff, so we're trying to solve for stuff. There's only one variable left, and that's concentration. Well, there's my concentration right down here. This represents my concentration. Now, because concentration is a ratio, we have to have a ratio and certainly show units. So this is something that we want to make sure we understand. For percent solutions, the units of percent are grams per 100 milliliters. For other things, for molarity, for example, if we were going to talk, if we had a problem about molarity, big M, and we'll talk about this in just a minute. Big M, the units of molarity are moles per liter. Again, it's just a ratio, stuff over volume. Going back to our problem, we have a concentration of 0.9%. So what does that mean? That means our concentration is 0.9. Oh, 0.9, and what are the units? Grams per 100 milliliters. Okay, now we can begin to understand how to do this. So, because we have our little algebraic homemade equation of concentration equals stuff over volume, we're trying to solve for stuff. Therefore, we just multiply both sides by volume, and we get stuff equals concentration times volume. Hopefully that makes sense to everybody. Our concentration is right up here at 0. This is going to equal then 0.9 grams per 100 milliliters. And we're going to multiply that by our volume, which is 500 milliliters. It's important to write units because I cancel units out, and that helps me know that I did it right. Milliliters on the top, milliliters on the bottom, they cancel out, and now all I have to do is my math. So 0.9 times 500 divided by 100, and we end up with 4.5 grams of NaCl that were in that 500 milliliter IV bag. Now, let's reverse this and let's try something a little bit more challenging. Let's take this value, 4.5 grams. How many moles of salt are in that bag? That's my next question. How many moles? Now, to understand this, we first have to define a mole. I've got a picture of a mole right over here. There it is. Perfect. There's a mole. But that's not what we're talking about, even though it is very cute. What we're talking about is a mole. And guess what? It's just a number. Okay? Don't let it freak you out. It's just a number. If I came across, or if I asked you what a dozen is, consider a dozen. A dozen is kind of a random word, but guess what? A dozen is just a number. It happens to be a number 12, right? We equate those two things. A mole is the same thing. It's just a number. It's a bigger number slightly, right? Now we're talking about 6.022 times 10 to the 23rd. It's actually a very ginormous number, which is why we simplify it and say mole, because I don't have to think about numbers that big. Nevertheless, it's just a number. A key point to understand here is here we have grams. That's a weight. Here we have a number. If I asked you how much a dozen weighs, what's your response? It's kind of a trick question, right? You're like, a dozen what? A dozen bowling balls weighs a lot more than a dozen eggs or a dozen feathers or a dozen large rocks, right? All of these things, the number doesn't tell me anything about the weight. So if I have 4.5 grams, how do I know how many moles are in there? The beauty of the periodic table is that I have my conversion factor. Remember, going back to our pizza analogy at the beginning, if I knew how many pepperonis there were and I knew the total amount of weight, then I could determine how many or how much one individual pepperoni weighs. That conversion factor, that same conversion factor, is actually given to me by the periodic table. So we're talking about sodium chloride, right? NaCl. Let's look at sodium and chloride. Sodium is right here on the periodic table. Chlorine is right here on the periodic table. And these numbers are important numbers, right? We talk about this atomic weight right here. Well, that atomic weight has two different unit measurements to it. We could talk about atomic weight in terms of AMU per molecule or per element, or we could also talk about that atomic weight in terms of grams per mole. And that is the most important number for us when we're talking about moles. In other words, hydrogen weighs 1.008 grams per mole. Chlorine, if we look over here at chlorine, number 17, weighs 35.45 grams per mole. So now we have our conversion factor. We can come back to answer this question. If we look at the periodic table, sodium weighs, we go look at it, 22, approximately 23, it's 22.99, we'll round, 23 grams per mole. Chlorine weighs 35 grams per mole. So if we add that up, we find that sodium chloride is just the sum of those two. That equals 35 plus 23, 58 grams per mole. Okay, now we go back to this idea of converting between grams and moles. How many moles are in 4.5 grams? Well, now it's easy. 4.5 grams times my conversion factor, which is 58 grams per mole. Do I put the 58 on the bottom? Do I put it on the top? We want to be able to cancel out units. So I'm going to put 58 grams per mole. Now I have grams on the top. It cancels out with grams on the bottom. And all I have to do now is my math, which is 4.5 divided by 58, and I get 7.76 times 10 to the negative 2, or well, that's going to be moles. We can express that in millimoles, which is 1,000, so that's going to be 77.6 millimoles of salt. Now, just to wrap that all up, if I have 77.6 millimoles of salt, what that means is that if 1 mole is 6.022 times 10 to the 23rd, then I could actually count out, if I counted individual sodium chloride molecules one at a time. I don't have a lifetime to do that, but it would come out to this many, 77.6 millimoles. It's just a number.